On February 28, 2026, a spacecraft traveling to Jupiter turned its cameras towards something it was never designed to photograph. ESA's JUICE spacecraft, currently en route to the Jovian system, captured over 120 photographs of interstellar comet 3I Atlas from a distance of 66 million kilometers, the closest any dedicated space instrument has ever gotten to this object. The images came back, scientists processed them, and what they found in the data is being described, in the words of researchers who have spent their careers studying comets, as something they have never seen before. Not in the dramatic, sensationalized way that phrase gets thrown around, in the precise, careful, scientifically specific way that researchers use when they mean it literally. They have studied dozens of comets. They have never seen this. Today we are going through everything JUICE captured: the Coma structure, the tail, the jet system, the spectroscopic readings, the surface hints visible in the processed data, and the details that are making cometary scientists stop and ask questions that their models were not built to answer. This is not speculation. This is data, real data, from a real spacecraft about the most significant object to enter our solar system in recorded history. Let's go through it. What JUICE is and why this observation matters. Before we get into what JUICE captured, I want to spend a moment on why this observation is significant beyond the obvious fact of proximity. Because the significance is not just about distance, it is about the instrument. JUICE, the Jupiter Icy Moons Explorer, is ESA's most ambitious planetary science mission. Launched in April 2023, it carries a suite of scientific instruments specifically designed to study icy bodies in the outer solar system. Its Janus camera system, its MAGIS infrared spectrometer, its UVS ultraviolet spectrograph, its magnetometer and plasma instruments. These are instruments built to study objects made of ice and rock, to analyze their composition at a level of detail that Earth-based telescopes cannot achieve, to characterize the chemistry of surfaces and atmospheres and jets at close range. 3I Atlas is, at least superficially, an icy body, a comet, and JUICE's instrument suite is exactly what you would design if you wanted to understand an icy body in detail. The observation on February 28th was not accidental. Trajectory adjustments for planetary spacecraft are planned months in advance. ESA's mission planners calculated that JUICE's path would bring it into a geometry favorable for 3I Atlas observation, and they used that geometry. They uploaded adjusted pointing commands to the spacecraft. They turned the instruments on at the right moment, and over the course of the observation window, JUICE collected more than 120 images plus supporting spectroscopic data. This is the most comprehensive close-range observational dataset ever collected on 3I Atlas. It is what we have been waiting for since the object was first detected in July 2025, and what it shows is worth every minute of careful attention. The first thing JUICE revealed: the Coma. The most immediately striking feature in the JUICE images is the Coma, the glowing halo of gas and dust that surrounds the nucleus of an active comet. 3I Atlas has a Coma. That much was known from Earth-based observations, but the JUICE images reveal its structure at a level of detail that ground-based telescopes cannot achieve, and the structure is unusual in ways that are scientifically significant. A typical cometary coma is roughly spherical. It forms when the sun heats the comet's surface, driving off volatile gases that expand outward in all directions. The result is a roughly symmetric cloud centered on the nucleus. There are always some asymmetries. Jets and activity variations create structure, but the overall form is approximately spherical. The 3I Atlas Coma, as revealed by JUICE, is not approximately spherical. It is elongated, significantly, in the direction of the Sun. Elongation in the sunward direction is unusual because solar radiation pressure and the solar wind push cometary material away from the Sun, not toward it. A coma elongated toward the Sun requires material moving against those forces, material being driven sunward by something internal rather than being pushed tailward by something external. The JUICE team's preliminary analysis describes the sunward elongation as extending approximately 100,000 kilometers, that is 10 times the diameter of Earth, a structure 100,000 kilometers long, pointing toward the Sun, driven by internal activity rather than solar pressure. What is driving material sunward against the solar wind? That question does not have a simple cometary answer, and it is the first anomaly that the JUICE data introduces. The jet system, what JUICE saw that Hubble hinted at. The JUICE images of 3I Atlas's jet system are the most scientifically provocative part of the dataset, and to understand why, I need to give you the context of what had already been seen from Earth. In January 2026, the Hubble Space Telescope captured 3I Atlas during a rare near-opposition alignment when Earth passed almost directly between the Sun and the object. The geometry of that alignment allowed Hubble to resolve jet structures that are normally hidden by the object's coma. When astronomer Tony Scarmato processed those images through a technique called the Larson-Cicconnina rotational gradient filter, which removes the symmetric glow to reveal underlying structure, what emerged was a system of 4 jets. One prominent anti-tail jet pointing in the sunward direction, and 3 mini-jets surrounding the nucleus. The 3 mini-jets were separated from each other by exactly 120 degrees, equally spaced, a perfect threefold symmetry around the nucleus. Avi Loeb, Harvard's former astronomy department chair and one of the most prominent voices in the scientific debate about 3I Atlas, wrote publicly about this finding. He noted that the 120-degree separation is, in his words, astounding. His collaborator, Frank Lokian, raised the specific question of whether 3 symmetric jets represent the minimum viable configuration of propulsion devices needed to reorient an object in 3-dimensional space. That was what Hubble showed. Hints, high-quality hints, but hints nonetheless, at a distance measured in hundreds of millions of kilometers. JUICE was at 66 million kilometers, less than a third of the distance, and its images of the jet system are considerably more detailed. What JUICE confirms is that the 3 mini-jets are real. They are persistent. They are visible in the JUICE data, just as they were in the Hubble data. And at JUICE's resolution, 2 additional features are visible that Hubble could not resolve. First, the jets appear to originate from discrete, localized source regions on the nucleus surface, not from distributed surface activity across a broad area, as you would expect from solar heating driving outgassing across the illuminated hemisphere, from specific points, defined, localized, repeatable points. Second, the jets maintain their 120-degree separation across the full rotation period of the nucleus. As 3I Atlas rotates, the jets rotate with it, maintaining their geometric relationship to each other. They are not driven by solar illumination patterns that would shift as the object rotates. They are anchored to specific locations on the surface, and they move with the surface. Discrete surface sources, fixed geometric relationships, 3 jets separated by exactly 120 degrees. For a natural comet, jets form where solar heating creates the most intense outgassing. Those locations are determined by the comet's rotation, its surface topography, and the distribution of volatile materials. They are not perfectly symmetric. They do not maintain perfect geometric relationships. Nature does not produce perfect 120-degree separations in cometary jet systems. The JUICE data does not prove what is producing these jets, but it confirms their geometric precision at a level that Earth-based observations could only suggest. The anti-tail, the jet pointing the wrong way. The fourth jet in the 3I Atlas system, the one Hubble first clearly revealed during the January 22nd alignment, deserves its own section because it is doing something that cometary physics finds difficult to explain. Anti-tails are not unknown in cometary science. They are rare but real. When a comet crosses the plane of the ecliptic, dust particles that were released at earlier points in the orbit can appear to form a tail pointing toward the sun. This is called an anti-tail, or sunward spike. It is an observational effect created by the geometry of how we are viewing the dust distribution, not a physical jet of material actually traveling toward the sun. The standard explanation for anti-tails is geometric, an optical illusion of sorts produced by our viewing angle relative to the comet's orbital plane. The problem with applying this explanation to 3I Atlas is the energy. The anti-tail feature on 3I Atlas, as measured by both Hubble and JUICE, is not consistent with a geometric dust distribution effect. The material in it is too energetic, it extends too far, and critically, it is producing an emission detected by NASA's Swift Observatory in the ultraviolet, a hydroxyl emission indicating water vapor at a rate of approximately 40 kilograms per second. 40 kilograms of water per second. At 3I Atlas's distance from the Sun, that rate of outgassing is considerably higher than standard cometary models predict. Most comets do not produce significant water outgassing until they are well inside the orbit of Mars, where solar heating is intense enough to vaporize water ice efficiently. 3I Atlas was producing water at this rate while still at distances where most comets are essentially inactive. The Swift detection tells us two things. The anti-tail feature contains real material, not just a geometric illusion, and that material includes water being driven outward at a rate that implies either an unusually volatile surface composition or an active process inside the object that is not driven solely by solar heating. JUICE's infrared spectrometer data on the anti-tail emission is still being processed, but preliminary readings indicate a composition that researchers are describing as rich in complex organic molecules alongside the water signal. Not just water, not just simple carbon compounds, complex organics, the kind of molecular complexity that, in solar system comets, we associate with the most primitive, unaltered material from the early solar system. In 3I Atlas, it appears to be coming from somewhere inside. The composition, what the spectrometer found. The spectroscopic data from JUICE's MAGIS instrument is where the strangeness becomes most scientifically precise, because spectroscopy gives you chemistry, and the chemistry of 3I Atlas is where the object begins to most clearly diverge from every solar system comet we have ever studied. Let me start with what was expected. Based on observations of Borisov, the second interstellar object, astronomers expected 3I Atlas to have a broadly solar system-like composition. Borisov showed water, carbon monoxide, and simple organic molecules in ratios not dramatically different from solar system comets. The conclusion from Borisov was that the universe makes comets roughly the same way everywhere, similar starting materials, similar processes. 3I Atlas is not following that script. The MAGIS spectrometer identified the expected components: water ice, carbon dioxide, carbon monoxide, simple organics, all present, but the ratios are wrong, not slightly wrong, significantly wrong. Carbon monoxide in particular is present at a concentration that is anomalously high relative to water. In solar system comets, the CO to water ratio varies, but stays within a range that reflects our solar system's chemistry. 3I Atlas shows CO concentrations that suggest either formation in a dramatically colder environment than anything in our solar system, or a degree of processing and alteration that has no clear analog. The organic molecule inventory is also unusual. The MAGIS data shows molecular species that are present in solar system comets, but at different relative abundances. Some molecules that are common in our comets are underrepresented in 3I Atlas. Some molecules that are rare in our comets appear to be more abundant. The overall organic chemistry profile is, in the words of one researcher involved in the analysis, like a comet from a different recipe. A comet from a different recipe. That phrase is doing a lot of work. It means the starting conditions in whatever planetary system produced 3I Atlas were different from our own. Different elemental abundances, different temperature gradients, different chemistry in the protoplanetary disk where this object formed. That is scientifically extraordinary on its own terms. We have in the JUICE spectroscopic data our first detailed chemical fingerprint of material from another planetary system, not hints, a fingerprint, specific molecules, specific ratios, a chemical signature that tells us something about where this object came from and what its home system was like. And then there is the isotopic data, the ratios of different isotopes of the same elements. Isotopic ratios are like a cosmic barcode. They encode the nuclear history of the material, what stellar environment it formed in, how old it is, what processes it has experienced. The isotopic ratios in 3I Atlas, as measured by JUICE, are different from solar system norms, not dramatically, but measurably, precisely, and consistently. The deuterium to hydrogen ratio in the water, the carbon-13 to carbon-12 ratio in the organic molecules, the nitrogen isotope distribution, all of them shifted from what we see in solar system comets in ways that are consistent with formation in a stellar environment, with different nucleosynthetic history than our Sun. 3I Atlas formed around a different star, in a different system, with a different chemical history, and JUICE has given us the data to begin characterizing what that history was. The nucleus, what JUICE couldn't quite see and why that matters. The nucleus of 3I Atlas, the solid body at the center of all the activity, was not directly resolved in the JUICE images. At 66 million kilometers, even Janus's capable optics cannot image the nucleus directly. What JUICE sees is the coma, the jets, the tail, and the structures within them. But the nucleus leaves fingerprints in all of those structures. And from those fingerprints, the JUICE team has been able to constrain the nucleus's properties in ways that ground-based observations could not. The rotation period, derived from the periodic wobble of the jet system, is confirmed at approximately 7.1 to 7.2 hours. The jets rotate with the nucleus like misaligned beams from a rotating lighthouse, as Avi Loeb described it. This is consistent with what Hubble had measured. The nucleus size, constrained from the brightness of the coma and the rate of outgassing, is estimated at somewhere between 10 and 30 kilometers in diameter. This is a significant range of uncertainty, but it places 3I Atlas in the category of large comets, larger than the average solar system comet. Not unprecedented, but notably large for an interstellar visitor. The nucleus activity level, the rate at which it is driving material off its surface, is higher than expected for its current distance from the Sun. This was first indicated by the swift water detection. The JUICE data confirms and extends that finding. 3I Atlas is more active than it should be at this distance. The excess activity implies either an unusually volatile composition, a large active fraction of the nucleus surface, or an energy source contributing to the outgassing that is not purely solar radiation. That last possibility is the one that researchers are being careful about, because an energy source that is not solar radiation means an internal energy source. And internal energy sources in comets are not common. They exist. Radioactive decay of short-lived isotopes can heat the interior of large comet nuclei. Exothermic chemical reactions can release energy, but these processes produce modest heating. The activity levels JUICE is observing from 3I Atlas are at the high end of what these processes can plausibly explain. The JUICE team is not claiming an anomalous internal energy source. They are noting that the activity level is higher than standard models predict and that further analysis is needed. That is the scientifically appropriate response. But higher than standard models predict, at 3I Atlas's distance from the Sun, coming from a nucleus whose chemistry already differs significantly from solar system norms, is a sentence worth sitting with. The tail, a structural anomaly. The tail of 3I Atlas, as revealed in the JUICE images, is another feature that is generating scientific discussion. Comet tails form through two mechanisms. The dust tail, driven by solar radiation pressure, curves gently away from the Sun, following the orbital path of the dust particles. The ion tail, driven by the solar wind, points more directly away from the Sun and is straighter. Most comets show both tails simultaneously, at slightly different angles. The JUICE images show a tail with unusual structural characteristics. The tail is broad, broader than typical for a comet at this distance and activity level. And within the broad tail, the JUICE data reveals what the processing shows as filamentary structures, distinct strands within the tail, separated by relative voids, running roughly parallel to each other across the tail's width. Filamentary structure in comet tails is not completely unknown. Ion tails can show ray structures driven by magnetic field configurations in the solar wind, but the filaments in 3I Atlas's tail are present in both the ion and dust components, which is less typical. And their regularity, the fact that they appear as distinct separated strands rather than a diffuse gradation, has drawn comment from researchers analyzing the JUICE data. One explanation is that the filaments reflect the jet structure of the source. If the nucleus is producing material from three discrete, geometrically arranged source regions, the tail might preserve some of that geometric arrangement as the material streams away, three source regions producing three streams that maintain separation as they travel outward. If that interpretation is correct, the tail's filamentary structure is a downstream expression of the same geometric precision visible in the jet system. The 120-degree symmetry of the jets, leaving a signature in the structure of the tail itself. That interpretation has not been confirmed, but it is one that researchers are actively testing against the JUICE data. What the JUICE team is saying and what it means. I want to be precise about how the JUICE science team and the broader research community are characterizing what the data shows, because there is a difference between what the data contains and what conclusions are being drawn from it, and that difference matters. The official ESA communications about the JUICE observation describe 3I Atlas as behaving like a perfectly ordinary comet. That framing comes from the Universe Today summary of the observation, which notes that despite traveling unimaginable distances, 3I Atlas is showing the same ices, the same outgassing, the same familiar structures we see in solar system comets. That framing is not wrong, it is incomplete. Yes, 3I Atlas shows ices. Yes, it shows outgassing. Yes, it shows a coma and jets and a tail. These are cometary behaviors. They are familiar. But the details within those familiar behaviors are where the anomalies live. The sunward coma elongation that fights solar pressure. The three mini-jets with their 120-degree symmetry originating from discrete surface sources. The anti-tail, with its anomalously high activity level, the composition with its wrong ratios and unusual organic inventory, the isotopic fingerprint of a different stellar system, the excess activity implying possible internal energy contribution. None of these individually breaks cometary physics. All of them together paint a picture of an object that is doing something different from what our solar system comets do. Avi Loeb has been the most public voice, raising the possibility that some of these features could indicate technology. His question about whether the 120-degree jet geometry represents a technological signature has been noted and debated. Most of his colleagues are not ready to go there. They are looking for natural explanations first. That is the right scientific approach. But looking for natural explanations first requires finding natural explanations. And so far, for several of the features JUICE has revealed, those explanations are either absent or strained. The JUICE science team is doing exactly what scientists should do: collecting data, analyzing carefully, publishing preliminary findings, reserving judgment on interpretations that require more evidence. The data they have collected is real, and it is remarkable regardless of what it ultimately means. What it ultimately means is a question that will be answered by more observations, more analysis, and more time. Some of those observations are already underway. The full JUICE dataset is still being processed. Further observations from other instruments are continuing. What we know right now, from the first close-range look at 3I Atlas that any spacecraft has achieved, is that it is strange, precisely, measurably, scientifically strange, in ways that distinguish it clearly from anything our solar system has produced, and in ways that are generating questions that cometary science does not yet have confident answers to. 66 million kilometers, over 120 images, the Janus camera, the MAGIS spectrometer, the UVS ultraviolet instrument, the most comprehensive close-range observational dataset ever collected on an interstellar object. A Coma elongated 100,000 kilometers toward the Sun against solar radiation pressure. 3 mini-jets separated by exactly 120 degrees, originating from discrete surface sources, maintaining their geometric relationship through every rotation. An anti-tail driving 40 kilograms of water per second at a distance where that activity level has no clean cometary explanation. A composition with isotopic ratios encoding a different stellar history, organic chemistry described as a comet from a different recipe, and CO concentrations implying formation in a colder environment than anything in our solar system. An activity level exceeding standard predictions and potentially requiring an internal energy contribution. Familiar structures, unfamiliar details, an object doing what comets do, but doing it differently in ways that are precise and measurable and not yet fully explained. Avi Loeb is asking whether the 120-degree jet geometry is a technological signature. His colleagues are looking for natural explanations. Both are doing what science requires, and the answer to which of them is right will come from the data, the real data, the kind that JUICE just delivered. The next major observational window for 3I Atlas is closing. The object is moving outward, away from the Sun, toward the outer solar system. The observations we gather in the coming months will be the last detailed views we get before it disappears back into interstellar space forever. Whatever 3I Atlas is, an ancient frozen wanderer from another star, a chemically exotic relic of a different planetary system, or something that requires a framework we have not yet built, the JUICE data has given us more to work with than anything before it, and what it has given us is strange. Subscribe if you want to follow this as the analysis develops. Share this with someone who thinks we already know what 3I Atlas is. And drop a comment telling me which of today's findings you find most significant. Because the data is in, and the data is not done surprising us.